presenting the topic, which is a primer on the inner workings of transformer-based language models. Uh, so in this presentation, firstly, I will cover what transformer model basically are, like what are the components of transformer-based models. More on the visual side rather than the written side. So we should get a good understanding by the end of this phase of presentation. We should have a good understanding about how we represent the transformer model or the architecture of transformer model in general. Then I will introduce you to a general idea of mechanistic interpretability and how we can do mechanistic interpretability in general. Then there are two major branches of mechanistic interpretability which can be performed on transformer-based language models, which are behavior localization and information decoding. So here I have listed both of them, but in this presentation, I would go just with the behavior localization because like there are three methods which I have to cover. And then if time permits, we can touch upon the method of information decoding. So that is the whole agenda or the flow of presentation, how I arranged it. Let's start with the first stage, which is transformer model, visual deep dive into how transformer model works. One notation thing here. So whenever I'm saying transformer model during this presentation, I'm strictly talking about the decoder only transformer models. So not the general idea of transformer, which was proposed in the first paper, attention is all you need, where you have a encoder and a decoder. For these language models, which are specifically known as generative models, we are talking about the decoder only model. So where the representations are already like pre-learned, and we have a representation matrix or an embedding matrix, which has the representation which are learned from some encoder task on the language. And then we directly use that representation with a decoder pipeline. So it's a decoder only pipeline where just model learns to use those representation to do downstream task. In this case, because we are talking about language models, so the primary task is linguistic modeling or like language generation. And then the newer model, definitely they can do a lot more than simple like text understanding. But for now, let's just keep it to a basic GPT-2 kind of architecture where the language generation or the next token prediction is the preliminary task. So that's a notation thing. Whenever I say transformer model, it would be like specifically decoder only transformer model, unless otherwise specified in the presentation. Okay, so let's start with the general flow of transformer models. Uh, the presentation is moving, right?
Yeah.
Okay, okay. Okay, so as we can see, let me just grab a laser tool. Okay, yeah. So as we can see, this is the general flow of a early language model or early large language models which we have. And this is like a basic structure of any language model, even the modern ones. Though the number of transformer block may vary, the way in which the embed the language or the words that may vary. The tokenization strategies may vary. They can have like multiple different kind of activation functions in them. Something like that, something like RLHF can be used for training the models, but more or less the general core architecture is this. So here the steps are that in the starting you have like a text or for a newer model any kind of prompt that will be given to a tokenizer. Now, the task of this tokenizer is to basically tokenize the text into small chunks or subwords. Like, so, a major misconception which we usually have is that each word in the language model is treated as a separate token, which is not the case. So, language model do have a limited vocabulary. For example, a GPT-2 model has a vocabulary of 50,267 tokens. So it would, sorry. So once we have given the text to the tokenizer, the primary task of tokenizer is to basically tokenize this text into some known tokens which it has already learned or which are in the vocabulary of large language model. And in that way, we get the tokens. Now, one other thing which I would want to highlight here, so this token T is a vector not of the actual word token. So, for example, if I say the capital of France is Paris, the tokenizer will tokenize it in something like the capital of France is Paris. So, like there are six tokens, right? But this T would basically map their respective position or their respective index in the model's vocabulary itself. So you would get something like 567, 268, 3400, something like these numbers. So they represent the index where this token is in the model vocabulary. So if the vocabulary is say of 50,000 word in general or 50,000 token in general, you can get any index ranging from 0 to 50,000 minus 1, right? So that is how this text will be converted into an array of integers or positions. Now from here, this array would be passed to two different embedding generation algorithms. So first is the on right side of your screen, you can see there is like word embedding, right? So this word embedding, as I stated earlier, are already learned by any like representation learning task, and we have a WE matrix here. The dimension of this WE matrix would basically be D vocabulary cross D embedding. So for each token in model's vocabulary, you would have a representation of D embedding length or D embedding values. For example, GPT-2 uses 768 as the D model or D embedding. So we would get a matrix. We would have a matrix of 50,000 cross 768. And so basically what we are doing is T multiplied by WE. This will pick those representation because T is a vector of index, right? So when you multiply this with like D vocabulary, what it will do is basically it will pick up those representation from these vocabulary points and then put them in a vector. So that would be our embedding vector, which is like X embed, which then goes into transformer blocks as the input. Now, the other part of this would go to the positional embedding generation process. Now, positional embedding, they are constant. So for example, they do not depend on the tokens, rather they depend on what the length of your text prompt or any other prompt is. Is it like six tokens long? So then you will generate positional embedding W0, W1, W2, W3, W4, W5, these positional embeddings. So expositional, or this W positional is basically a vector of size D context cross D embedding. Now, why D embedding? Because we are going to concatenate these two embedding vectors here. So that's why they have chosen to keep the dimension of your positional encoding same as the dimension of your actual word embeddings, which you have learned. And D context, because this, for example, the context length for GPT-2 is basically 1024, right? So for each of these positions, so you can't go beyond this position, the model will throw an error that this is out of the context length, right? So you can go up till maximum of like 1024 token in a prompt. So for each position, there is a fixed positional embedding that has already been like pre-generated and kept in this kind of WPOS kind of a matrix, or like a vector with which have a dimension of D context multiplied by D embedding. And again, you will basically, based on the length of your token, which is T here, you will choose the starting first T positional embeddings and then concatenate them with the word embedding. And this is the first, like the we call it like residual pre. It is basically the first input which we then give to the transformer block. So this will formulate the base input for your transformer model. So this process, there is like no training involved while you are training a language model. So when we are training the language model, these things are basically pre. So you would get a pre-trained tokenizer. You would have WE and W pause created and kept for you. We will just call these values and prepare this input. So this is like an input processing. If you want to relate that with computer vision kind of a task, this would contribute to the input processing stage of a computer vision task. Then comes the transformer block. So I will explain.
Meher,
Yeah,
sorry for
hi.
interrupting. I just have one question. So this may be basic, but I'm new to this. So, here you are representing tokens as a T. That's a vector, right?
Yeah.
And then X embedding is equal to T dot WE. WE is a embedding vector
Yeah.
or a
So, yep. Yeah.
yeah. So, what's the dimensionality of X embedding?
Yeah, so the dimensionality of X embedding. So first of all, T dot WE does not mean we are like doing a dot product here. It's
Okay.
just, it means that we are choosing. So T, as I said, would have these index in it. For example, it would have something like 265, comma 3500. So those index are basically
Okay.
where the token is in the D vocabulary.
Okay. Okay. So
So
D vocabulary is fixed, and like
yeah, so D
the token.
vocabulary is like if you have 50,000 tokens as your vocabulary of model, you can have index ranging from 0 to 50,000 minus 1, right?
Mm, mm-mm.
49,999 to be
Yeah.
precise.
Yeah. Yeah.
And this T, so basically text tokenizer will do two things. It will first of all tokenize the text based on that vocabulary, but it won't give those text like raw text tokens forward to the model. It will convert those tokens into their corresponding position in this D vocabulary. And what I
Okay.
mean by T.W is basically choose these index from W vocab, like D vocab, oh, sorry, the WE. Now, as you asked, what is the final dimension? So now we are choosing T points from WE matrix. So the final
Mm,
resulting vector would basically be of dimension T, like T basically cardinality of T multiplied by multiplied by models embedding shape. So T cardinality of T
okay.
multiplied by D embedding. So instead
Okay.
of D
So.
vocabulary, you would have like
Mm,
selected points of D vocabulary now.
okay. Okay. So W is like a embedding vector that has word embedding for all the 50,000
Yep.
50,000 tokens in our vocabulary, and then
Yeah.
by X embedding is equal to T dot W, you are like denoting, we are selecting the respective embeddings for
Yeah.
the
So
tokens that
a
we have
more
in our context.
precise code operation would be WE, and then you put a list sign there, and then you call those T indexes out of it.
Okay, okay,
So
okay,
a more precise coding part would
okay,
be that. This is just to
okay,
depict that because that would become
okay.
too complicated for the normal
Yeah, yeah,
depiction
yeah,
here.
yeah, yeah.
Yeah.
Okay,
But the
okay.
And
idea is
the
to
and the plus operation is just an addition, right? It's not concatenation.
Yeah, it's an addition. So you add, so it's like a element-wise addition. So you would add the first
Mm,
token's word embedding with the first token's positional embedding. You would add
mm,
second token's word embedding with the second token positional embedding.
mm,
Mhm.
So your HO will basically result in a vector which has a size of, again, T cardinality multiplied by D embedding, because we
mm,
have on the both the sides we have T such
mm,
tokens,
mm,
and the dimension of their representation, both the word embedding representation and the positional embedding, is D embedding. So when you add all
mm,
this, it
mm,
would
mm.
remain the number of tokens
Okay,
multiplied by D embedding, whatever
okay.
your embedding dimension is. And also as a notation, like a side example here, like in notation generally, if you go through the papers, you would find the authors using D model instead of D embedding, but that
Mm,
exactly means the same thing. So D model and
mm.
D embedding, it's same thing. We can use them like interchangeably.
Okay, okay.
Yeah, because I also might use D model later on sometime while discussing this. Okay, so till here we have prepared a basic input of size T, like number of tokens multiplied by D embedding. Now this what I'm explaining is for like one prompt. Now you can batch these prompts, so that would basically become batch, comma. Uh, so what I'm saying, number of token becomes sequence length. So you would say batch, comma sequence, comma D embedding or D model. So in reality, the actual dimension of H0 would be batch, comma, sequence, comma, D model. And in a lot of papers, if you go through the papers regarding either mechanistic interpretability or basic transformer models, they use this kind of dimension. Now here I am not using the batch dimension because we are just like I'm depicting it to be processing a single prompt at this step. So the batch size would basically become one, but you can basically concatenate different prompts in a batch, like 2 to 4 prompts while training to increase the efficiency. Now, this goes into transformer blocks. Now, as of now, we are treating the transformer blocks as like a modular operation here. I will explain transformer block in upcoming slides, but as of now, this will basically go through n such transformer blocks. Now, in the starting models like GPT-2 or like GPT-J kind of models, there were like 12 to 32 transformer blocks. In newer model, you would get a lot more transformer blocks. You can get till like 64 transformer blocks or anywhere up to like 100 even transformer blocks, something like that. So again, but it you can choose based on your size of your model and how much capability you want to have with the model. The final, so the fine, so basically what will happen is all the operations which will be done in the test transformer block basically would keep will basically keep intact this dimensionality. So in the end, you would get an HN with same dimension but a transformed vector. So which have all the information associated with it, whatever model has processed in the transformer block, but it won't change the dimension. So this hidden state which we have started at H0. So if after first transformer block it will become H1, after second transformer block it would become H2. In GPT-2 after 12 transformer block it would become H12. But the dimension won't change. Now we want to reproject this again over the vocabulary because we want the prediction. So the primary goal of the model is to generate a probability distribution over the vocabulary, and whichever token has the highest probability would basically be your next token prediction, right? So in order to do that, we will basically project it over an unembedding matrix, and the whole idea of unembedding matrix is to basically convert the D model dimension into D vocab dimension again, right? So now you have a D vocabulary over which it will project your input matrix, and those will be your logits. And you, sorry, wait, what? Yeah, okay, yep, sorry. So, and you will basically project or like pass these logits now through a softmax function to basically model probability between 0 and 1. And then based on the probability, we will sample the prediction. Now, there are different ways of sampling prediction as well. Normally, like in greedy sampling, you can just sample out the token with the highest probability, but sometimes it causes the model to like stuck in a loop. For example, if you're trying to generate like a sequence of A, B, B, C, C kind of a random sequence, it might just stuck with A because it is getting highest like high rewards for just generating some random token. So to avoid that, they do more probabilistic sampling based techniques which are applied to sample the model, and that's where the whole idea of your the major hyperparameters which we used while generating model response like temperature and K, top P, these are basically hyperparameters which affect the sampling process. So for example, top case based sampling, you would sample out the top case, for example, top 100 logits, and then renormalize the probability over those 100 logits, and then choose the final probability. Because sometimes it might, and in most times it happens that the vocabulary is very large. For example, 50,000 words here. So your probability distribution would be very steep because say for 15 tokens, you have approximately 99% of your probability is assigned to those 15 token, and then the remaining 1% of your probability is getting assigned to other tokens, right? So now if we sample out, say, top 50 tokens and renormalize the probability, the difference between probability of top 5 token would be much larger and much clear than what it should have been when you were assigning like 99% of probability to 15 tokens and 1% probability to other like remaining tokens. So that's how top K sampling work. There is also top P sampling or nucleus sampling, which is like based on the probability then. So these are basically the hyperparameters which are related to the sampling process. And after successful sampling, you will get a token, which is our next token prediction. And to generate a long sequence, then this token will be concatenated back into this text. And the whole text will again given to the model, and this whole process will be done again, and the next token will added here, and it keeps happening till either you have reached your max token generation hyperparameter, or you reach an end of sentence token. It's like a special token which signifies that the model has answered what you have wanted it to do. So something like that. So, any questions on this slide? I know I've spoken a lot here, so if you have any questions, just please go right now. Otherwise, like we'll lose the context when we move forward.
I have a question,
Yeah.
if I may. So, like if we just disregard batch size for now, the H naught vector is going to be the whatever the number of tokens
Yeah. So
times
sequence
the D
multiplied by
model,
de-embedding. Yeah.
and logits is at the end the logits is equal to Hn times WV. Then the output is again going to be the number of token, and it will be the number of rows, and then the number of columns will be the dimensionality of the model. Then, like for each row, there will be a number distribution which signifies the probability of that token being output, right?
Not really. So again, this is not like a dot product with what we are taking. What this depicts here is that you have a hidden state, and you will project that hidden state, or that the hidden or the logits. You will get it by projecting the last layer's hidden state over WU, which has the same dimensionality as WE, just the reverse
Hmm.
of that. So it would be de-embedding multiplied by de-vocabulary.
Hmm.
So in that way, what you will get is a probability distribution over the entire vocabulary. So what we
Hmm. Hmm,
want
hmm.
here is a vector which is of length d vocab.
Okay.
Yeah.
But number of okay, then there'll be just one token output from here.
Yeah. So that there will be just one token output. So in general, when you process it, there will be n token output, not one token output. The reason is that for each position which is already there in this thing, so it would basically become t multiplied by d vocabulary.
Yeah. That's what I was thinking.
So t multiplied by d vocabulary is what you will get. And here t represent the next tokens. For example, for the first t here will represent what model has predicted in the second position. But we already have the second position in our text. So what we'll choose from here
Okay.
is the last row.
Okay.
And
Okay.
we would discard all the entire row. But because model is trained for next token prediction, so it won't just predict the next token on last position. It will predict next token on each position.
Hmm.
So you would get t multiplied by d vocabulary as a vector. We will choose the last row from here because we want the next token prediction on the last position.
Okay, what happens if whatever we predict from the second to the final one is not matching with the original input? That means it's a
Oh,
bad model, or
yeah, I mean, it may happen as well. And it sometimes signify it is a bad model, sometimes not, because there are different like ways of like for formalizing a sentence, right? So as
hmm.
long as it is getting the actually next token which is correct, you are happy with it. So usually when you
Mm,
test the accuracy, you won't check tokens at position 1, 2, 3, 4, 5. You will just check the token like the last token
mm,
at the last position. But yeah,
okay.
so like this is a very basic architecture. In newer architecture, so if you want to go, you can go through like KV caching things, something like that. So they will cache the previously computed inputs or previously computed values, and then you don't have to compute a token, or you don't have to compute the vector which has like the dimension of t multiplied by w, sorry, t multiplied by d vocabulary. But in the basic vanilla architecture of like GPT based model or any other generative model, this
Mm,
is how you were doing it. So you predict token for each position in your prompt or in your
mm,
text, but you choose the next token generation, or you choose the distribution for the last position only, because that's your position of interest. So you want to generate next token on that particular position. So you just choose the last row of this logit, and then it would become 1 cross d vocabulary, and then you pass that 1 cross d vocabulary with a softmax, then it would become a probability distribution over the entire d vocabulary, and then based on
mm,
any kind of sampling method you can just sample that out. So
mm.
I hope that's clear now.
Yeah, okay. So go ahead. Like I have further questions, but I think we can discuss it later. I think.
Yeah, so any other question from anyone? All right. Okay. uh, Stuck in the presentation. Okay, yeah. So now this is basically a general representation of the transformer block. So transformer block, wait, what's happening? Okay, okay, sorry. So this is basically the general representation of our transformer block. So each transformer block in those n transformer block basically comprises of two layers. One is a multi-head attention layer with n different head, each head performing self-attention, calculation of self-attention over it, and then you just concatenate the entire or the like output vector of all multi-head attentions. And then the second layer is an MLP layer, a single multi-layer perceptron layer, which then applies an activation function over the vector which you have calculated through the multi-head attention, and then gives the hidden states for the next layer. So for example, if HO, which in this case I have depicted as XI for the IS transformer block, input I for the IS transformer block goes here. We first of all, we apply the layer norm. I will explain what the layer norm is on the next slide. After applying the layer norm, also let me just get a pen so you guys can follow. Okay, right. So after applying the layer norm, we will give the xi to all the heads which are there, like n heads, and then we will just concatenate the entire output of these different like these n self-head attentions. So we call it multi-head attention in the end, and then just give it back to the resolution. Now, this is a very important concept regarding the mechanistic interpretability of transformer models. So the general assumption or the idea here is that all these operations are like linearly additive. So for example, xi plus 1 here would basically, so xi plus 1 would be somewhere here. So xi plus 1 would be nothing but the value of xi, or the vector xi, plus whatever the concatenation of all the self attentions was there. And then you just add it back here, and that would become your input for the next layer. And then you again do a layer normalization over this. You give it to the MLP layer, and whatever vector that would give you, you would just add xi plus 1 with that, and you would get xi plus 2, which would be the hidden states or the input for the next I. So if this is x1, the final x2 would be basically this thing. I have say I have depicted it with xi plus 1, xi plus 2 for like clarity of like where we are computing or where we are concatenating the outputs. But in the end, this thing basically will be done in one single layer of transformer block or one single transformer block. And if you give like h0 to this, you will get h1 as xi plus 1 plus m x1, and that x1, if you want to even for if you want to simplify it even more, it would basically become m function applied over xi plus all the heads, all the self attentions combined. So that's the very basic or like very crucial underlying assumption, which a lot of interpretability methods later on like they uses to like uh, kind of decompose different paths in the LLM. So for example, if I close this connection and this connection, I would have a direct path to the next transformer block. So if I don't want any of the heads in this particular transformer block to be basically added, I can just have like a zero activations here or like a very low value of activation. And because of that, this plus operation would become insignificant and it won't change the vector at all. So it is as good as closing a connection here or closing a connection here and just have a direct path to the next block. Or for example, even on a more uh, internal level or more modular level, if the activation for like h0 and h1 and so on, like so for example, except for h2 h1, assume the activation for all the other heads to be very small, then what it is essentially doing is basically the path would go through h1 and then come back here. So we can decompose the path which model has used or like which heads and which neurons the model has used to compute this particular, sorry, this particular response or this particular answer. Because the all the large language model, they have so many number of neurons and like in MLP layer and so many different heads. It is not necessary that each head and each neuron will basically contribute for prediction of answer. They might embed different operations, they might embed different concept, and they may fire for different tasks. So this kind of linearly additive assumption or linear that the transformer model basically works in an additive manner where you can just add things basically helps us a lot to figure out which of the component or which of the neuron is basically active for a final answer prediction. So any question in this? All right. Oh, you were saying something?
No, go ahead, go ahead.
Okay, great. Okay, so now comes with so first of all, I will just explain what the layer norm is. It's nothing but like normalizing the input over the D model or the D embedding so that you have just a second. Also, I would be referring some of my notes here, so I might not be able to maintain a constant uh, camera facing here. Okay, yeah. So basically, layer norm will normalize the input over the model's dimension or the feature of the model, if you want to call. Like de-embedding have like 768 dimension in GPTO, so you can call them like each dimension a feature, right? So it would basically normalize over the entire model dimension. Why we do this is that to make sure that the residual stream, when we add this vector back to the residual stream, have a zero mean and unit variance. So basically it follows a normal distribution in the end. And that is exactly what you are doing. You will calculate a mean, you will calculate the variance, and you will basically, this is the computation where you will just subtract the mean and divide it with the variance. This small epsilon is to make sure that you are not doing a zero division error. Now, we also see this gamma and beta are basically translation and scaling. So this is scaling part and this is translation part that has been introduced because sometime your values would become like very close to zero and they diminish. So to avoid that, you always scale your vector back after doing this operation, because if your vector already have a very small, like a distribution which is very close to normal distribution, when you will basically subtract the mean from it and you divide it by variance, the values would become very small. So to basically maintain the processing further, or to keep the processing further intact, we'll scale it and just translate it. And these are also hyperparameters which are given to the model. So this is nothing which model learns. These things are fixed already. So for example, we can just call them like W and B. So it's like multiplying it with linear weights and then adding a bias to it. So it's basically a linear transformation of your mean operation, just to keep the values in the range and not letting them diminish after the process. Also, one question which a lot of people ask is that why use layer normalization? This is replacement of batch normalization, which is being used in like which have been used in the convolutional neural network. The reason for that is that this kind of layer normalization permits us to normalize individual prompts or individual sequence over the D model, rather than relying on the batch, or rather than relying to basically normalize the entire batch. The reason is that you usually do not know the batch size, because you can have like, or what I mean by you do not know the batch size is that if I am batching four text prompt or four sequences, the length of these sequences might differ a lot. One sequence can be of length 6, one sequence can be of length 16, right? In images, we always have a fixed dimension for the image. So if I'm using a model, I can fix my dimension to 256 to 256, and the entire batch would have the same dimension. So I can perform. So when I'm computing the mean and variance, that would basically be over fixed dimensions. Whereas if I just try to do that in a sequence, like in a batch of a sequence, that can be totally different for two different sequence of different length, right? So instead of doing that, we just normalize each prompt or each sequence in the batch over the D model using the layer normalization here. So that is like, and to be very precise, this is my understanding of layer normalization. I may be like little wrong here, but like that is how I understand layer normalization. That it's doing similar thing to batch normalization. It's only that we can't have that like liberty of specific or fixed batch size here. So we just normalize each sequence over the D model here. So you can do this for a batch size of one as well. Whereas if you want to do a batch normalization over a batch size of one, it would like fail miserably in the vision models. Also, like if anybody else has any information over layer normalization, please go ahead.
Oh, just a one quick question. Like as you said, like gamma and the beta are parameters, right?
Yeah.
So as we know in normalization, we usually do the difference with the mean and then the standard deviation at the
Yeah.
bottom, right? So is there any specific significance of gamma and beta parameters in this?
Yeah, so basically the
Mm-hmm.
thing is if your sequence is like very small sequence
Mm-hmm.
and it's the value, the x is very close to ex,
Mm-hmm.
when you do
Mm-hmm.
this and divide it with the variance, and if
Mm-hmm.
variance is already like very close to 1,
Yeah.
you would end up with a value which is very small,
Mm-hmm.
right?
Okay.
And if you
Yeah.
keep doing, because we are doing two layer normalization in a single transformer block.
Mm-hmm.
So imagine we are doing 12 transformer blocks, there were 24 layer normalization.
Mm-hmm.
So after some time, your vector would become 0.0000 something,
Yeah. Mm-hmm.
0.00000 something. So
Mm-hmm.
to basically avoid that, you just scale it back, or like just
Mm-hmm.
do a linear transformation of that to basically
Mm-hmm.
make sure that it stays in uh, a processable range for the
Okay.
computer.
Mm-hmm.
I mean,
Uh,
again, that is my understanding of it, because there
Mm-hmm.
is not much literature over
Okay.
why they have gone with this formula.
Mm-hmm. Yeah, beta and the gamma
Yeah.
thing. Okay.
I guess Anand,
uh,
have you like you were going through a paper which describes like layer normalization and batch normalization. So if like, you can comment on whether I'm like right or wrong.
Yeah, so I will
Mm-hmm.
just share the paper instead. They're just showing where batch norm is better, where layer norm is better. So it's mostly because of memory constraints, you're not able to use batch norm well, because for batch norm to work well, you need a big batch size.
Yeah.
And layer norm also gives you some other good properties when your all the values of the features are normalized.
Yeah,
Mm-hmm.
I mean, also like you can't do batch norm on like different of a batch of different sequence size. I mean,
Okay.
that
Yeah,
can
but
vary.
but in this
Mm-hmm.
case, in language models and all, you won't have a sequence length of uh,
Mm-hmm.
different lengths, because you'll be using padding
Yeah, I
of
mean, you
everything,
can use, but like for inference
and
time, it might not work.
no, it would still work, because after each transformer block, you would still be getting the same
Same
dimension that
thing.
was.
Yeah.
So
Yeah,
the
I
D
mean, yeah,
model
you
will
can use
remain
like
constant.
padding tokens for
So
that.
yeah, so D model will be constant. So that's why you
But like,
could
won't
use.
the zeros which you have added in the vector would affect the batch normalization if you try to do a batch normalization over a padded batch? Because the padding would
It might.
also be different. Like, I can pad a sequence with two zeros and I can pad a sequence with 20 zeros to make them like of similar sequence size.
Yeah, it might affect that, but it's batch norm, so we don't know. But it's mostly because of the
And also, like for batch norm to work, we need a batch size of at least like 16 or something, right?
Mm-hmm.
yeah.
A big batch. Like, as far as I know, it won't work for batch sizes like one or two, because then you are not normalizing it over the batch. It's like two tokens, so you won't be able to calculate a good mean or variance anyway.
Yeah. So there are different kinds of normalization. There's batch norm, there is layer norm, there is group norm, there is
Yeah.
instance norm.
So
So
in like
there are
in
different
modern
kinds of
models, they are
normalization.
kind of using group norms now, right?
Yeah, so they started with layer norm, then they moved on to group norm, and some people are even using instance norm.
Okay, yeah. I mean, I haven't gone through that, but like I know the names. So if you can share the paper, we can have a discussion over it.
Yeah.
Yeah, I'll share the paper after this.
Yeah. Thank you.
Meher, I have a follow-up question. So,
Yeah.
here, like, if the x is very close to mean, all that, like, if we have a sequence and then the x is close to mean, then its variance would be very small. And once you divide it by the root of variance, it will be like stretched. So if x is close to ex, most of the data points x is
Yeah.
close to ex, then variance would be small. Once you divide by ex, it will be stretched. That means like it's like standard normal distribution that we have for the z score and stuff. So if you raise this for a statistic to the power of negative, then it will be a standard normal distribution. That means
Yep.
the x being close to mean shouldn't affect it shouldn't have it, like we
Yeah, I mean,
dividing by
you
variance
are
we are
right. So I mean,
removing that
for
effect.
a
So
single sequence, it should not, but it
yeah.
might happen that for like if you have different, as you are talking about, the layer norm is normalizing over like sequence for one sequence over the entire feature. So that may vary for like sequence to sequence, and like assume that in order to basically keep it like standard and to make it more like uniform across all this processing, they have gone with this translation, like linear transformation. To be
Mhm.
honest, I never understood like why this is required, because
Yeah.
it's kind of a thing where in most of the paper it is stated that this is a design choice based on the model's performance. So they have tried like removing this, and the model performed like badly.
Yeah,
So
there must be some
this is
reason they are doing this, and like
yeah, I mean
this
the
gamma and
normal
beta.
reason is that you just apply a linear transformation to keep it like uniform across all the sequence and all the batches. But there should be some mathematical explanation of why this operation basically uniform it across everything. So yeah, I mean that would be a important topic for us to basically discuss
The gamma and
further.
beta, is it like, let's say there are different transformer blocks and they have different like multiple layer norms between them. So this gamma and
Yeah.
beta is staying constant, or they change between
No, no,
the layers?
they stay constant as per my knowledge. Yeah.
Okay, okay.
I mean, these are the hyperparameters. So like the parameters which are like you said, for example, you have a D model which is already a design choice, right? That we would keep 768 dimensions, right?
Hmm.
So again, the gamma and beta are something of that sort.
I think in batch norm, gamma and beta are learned.
No, so
So
I mean
gamma,
it is so gamma and beta again, so it's like W and B, so a weight and bias. So it would be learned when you are training the model, but once you have trained the model, that will be a parameter. So now for inference, that would be so when we are passing a token and inferencing it, it would be the weights or the parameters which are frozen.
Mhm.
So for generation task, that would be a or not a hyperparameter, a model parameter.
Mhm.
But like for example, when training, you will train these two like W and B matrices.
Hmm.
Mm.
And very similar to how you will train QKV as well. So when I go to next slide, we will go over the self-attention. So very similar to how you will train QKV. So QKV matrix is so the linear transformation for generating a query vector, key vector, and a value vector is learned while you are training the model. But once you have trained the model for inference, that would be like a static thing.
Hmm. Uh, Thanks, Mehar. Well, let's just one basic question. Sorry for interrupting. This X here, like X, it's a random variable that we are like calculating statistic. Like that is, what is it? Is it like each entry in a hidden state? Let's say if we have HN,
Yeah,
then
so
it has
it's
X1,
the
X2,
it's the
X3.
hidden state vector, and then we are computing the mean or like expectation over it.
X is a vector. You mean X is a hidden state vector?
Yeah, X is a hidden state vector. So basically, X
Uh,
here it is depicting it's a batch, comma sequence, comma D model.
so there won't be a batch in this, right? Or you,
Yeah, so in the implementation which we are talking about, there won't be a batch.
yeah,
But if you have, so for inference, you
for
won't have a batch. For training, you would have a batch.
yeah, that's right.
For training, you would have a batch. And so in training, it's slightly different because you would have a batch and you would try to learn this. While inference, it won't have a batch if you are using a chat completion kind of a setting. Sometimes when you try to like give model multiple tasks, it might also like you can batch things and then send it for inference as well. So yeah, that may work as well. Okay. Uh, why is not why are my slides not moving? Okay, yeah, it's moving now. Okay. So now let's talk about the self-attention layer. So I would explain a self-attention layer for like a particular head HI. And in multi-head attention, basically n number of these heads would be in a single attention layer for multi-head attention. So the internals of a particular head would be same. So assuming this to be a single text, I have omitted the batch size here. So you can just add batch to every dimension if you are doing it over batch or like if you are doing it for training purposes there. So this reside P pre is basically the xi which I was talking about in the residual stream slide, right? So now this, can I have to do this? Okay, yeah. So this will basically be given to these three linear transformations. So these red things are basically parameter of model, which are learned by the model. So we have WK, BK, we have WQ, BQ, and we have WB, WV, BV. So these are basically the parameters which model have learned. And what basically is happening is you are doing a linear transformation over the input vector here. And you would get key vector, query vector, and value vector. So this is basically QK and V. Now, intuitively, what query, key, and value mean is that query, for example, each token in your sentence wants to know what uh, the information other position or what relevant information other position have. So it's like a very good way to basically understand this is, for example, we have asked 5 people to stand in a row. Each has a plaque or a page or a cardboard or a board in their hand with a word or a token written over it. The constraint is that they can only ask the person like which who is right side of them about the information which they want to like which they have to understand in order to fully recover the meaning of the sentence. So query is basically each token position or like each position trying to send a signal to other token position that I want to know this kind of information or I want some information. Key, as the intuition goes or as the story goes, would represent a, a response signal or a feedback signal from other token position to a particular query position, whether they have the relevant information or not. And the value is basically the actual information which this query position or the query people or the person at the query position, a particular position wanted. And then they can basically recover what is important to them. So not the entire information is always important for a particular position to answer something, so like to understand the meaning. So they can basically just try and figure out what is important to this particular position. And keeping that story in mind, we can understand how attention score is calculated. So basically the attention is Q. So we can just, this D head is again to normalize the dot product of these two matrices. So that's like an operation that can be done over a vector. The main concept here is Q multiplied by a Q dot product K transform. So now, and also like these would Sk and Sk. So these like Sq is equals to Sk here. So these both will be a vector of same dimensions. So you are kind of multiplying two vector with same dimension. You just like, so when we are doing a transform of this, that will basically become Sk multiplied by Sk comma H multiplied by H comma Sk. So you would get a vector or a matrix with Sk cross Sk embedding, or not the embedding, Sk cross Sk dimension. So that would be basically this Sk is all the positions here. So this is sequence and then sequence K and then sequence Q. So this is basically nothing but the sequence, right? For example, if we go here in causal masking, we can see it's like 1, 2, 3, 4, 5, 6, 7, 8, 9 cross 9 matrix, right? So that means that the text or the input was basically of 9 tokens, or the sequence was 9, right? And what it will represent is for each, so like each value of this particular vector will represent how much a key position, for example, if I'm talking about this particular token here, like the first token, in all the key position, which position is like important. So like in all the key position, which position is important for like this particular token or this particular position. And that is what we call the attention score, like how much relevant the information at some other particular position is relevant for this particular position. So that's the intuition behind it. Mathematically, it just multiplies these two, and these are basically learned while we are training the model. So you can say that we don't have a verification method to basically verify our intuition, but the way these parameters are learned is to kind of enforce this intuition over the attention score calculation. Now that AI would again be of like SQSK, which is again same as the token length. So you would get a square matrix here of sequence cross sequence. Now, when we calculate this, we will calculate the query and key position relevance for tokens which are ahead in the sequence. For example, a token at the fifth position can also, sorry, token at the first position can also look at the token at the fifth position. It can ask token at the fifth position that, okay, what the information is, just to try and like cheat on the question, right? So that I can see in the future and I can just have that information prior to me. But the idea of the large language model or the language model in general is to basically predict the next token or predict the future token. So you don't want them to be looking into future and having that information before generating the next token or before generating the token which is right next to them, right? So that's why we applied the causal masking. So causal masking will basically force this square matrix to become a lower triangle matrix here. For example, the first token can only pay attention to itself. It has no other option, or it has no method to basically see any other position or extract any information from any other position in your sequence. The second can do it for itself and the first token because it's the second token. So it can have the information from the past, which is already being generated in the time, in the real time, but it cannot have information from its future. So this is known as causal attention. That's why the attention mechanism in the language model is known as the causal attention. And then this will basically be passed to the softmax function. So for example, this always be a 1 because there is no other value here. So the probability distribution for the first token will always be like it can only pay attention to itself. It can only extract information from itself. So it will always be a probability of 1. Here, those probability can be different. For example, this token might be paying attention to this token here, this token here. In this particular example of causal masking, every token is paying attention to itself, more or less, right? So most of the probability will be assigned to the diagonal. But in different cases, they might pay attention to different token. For example, in another case, every token might pay attention to the first token. Those are some heads which occur in a language model in early layers, and those are very important for the induction reasoning kind of task where model learn from the context of your data. So to keep the context, each token will just pay attention to where the sentence starts and how am I keeping the context intact. So it might differ based on the task in hand of what the head is being trained for. So this particular head, what it is being trained for, what kind of attention it has learned. And based on that, it can generate different orientation or variation of this kind of causal matrix, but it would always be a lower triangle matrix just to make sure that each token have opportunity to either pay attention to itself or any other position which is previous to it, or or the information that was already there before the generation of this token. Then that is basically passed through a softmax to convert this entire raw values into probability. And now we would have a vector where this row would become something like 0.01, 0.01, 0.01, 0.01, and 0. Something 998 something, right? Then when you multiply the v with it, it would have the value, it would pay most of the attention to the value of the token at this position. Now, here it's like current token attention. It can be different. Like it can be this position based on the task, what the text was, what the position was. So that may vary. But again, so that's the whole idea. So you basically have this V vector. You transform this using a WO vector. You do a linear transformation here, and then you just like perform the WV dot WO thing, and you will get the attention output, which is known as Z. So if you are trying to use libraries like transformer lens or logit lens to basically interpret the model, this is known as your Z component. So you can have the Q component. So you can actually have hooks around these component to basically extract this particular vector out, for a particular prompt and see what was the content of this vector. So this is known as Q, this is known as K, this is known as V, this is known as attention, ATTN abbreviated, this is known as Z. So we can have 5 different hooks in this kind of self-attention layer to basically see what is happening in the layer. So from mechanistic interpretability point of view, this is Z, this is V, this is Q, this is K, and this is attention. So attention would give you the hook which lies here, not here. Just to be clear about that. Questions? Also time.
Yeah, just go ahead. Yeah.
Sorry, it's taking a lot of time to go through this. I'm really sorry.
It's fine.
Okay, so this is the last thing. So again, so this is the MLP layer. What MLP layer does is basically it will, so it's a feed forward kind of a layer with like single layer of neurons, which is there. What they will, so it is like three, so you would do 3 operations in this layer. First of all, you would have a hidden state with batch size, sequence size, and D model. There would be a linear layer which will project this D model to DMLP, and this DMLP is equals to 4 cross D model is a convention. So there is like no particular again. So there is no particular reason for using 4 multiplied by DMLP. It's based on the ablation studies which are done on the experiments which people have performed, and they found that 4 multiplied by D model is quite a good dimension for your activation function of the neurons which you have. So basically, there would be one linear layer or one operation, linear transformation, which is performed on your hidden states, which will convert this into batch, comma, sequence, comma, DMLP. In DMLP, so here you will apply a Gaussian error linear unit, a Galileo function. I have described this function over here. Again, why we are using this? Uh, in the original transformer, also in the original GPT paper, they call it like a divine miracle or divine bliss, to be very honest. So they also didn't know why they were using it. They tested like 3 4 activation functions like variation of ReLU, and this was the one which was working. But there are paper after that. So there are 1 or 2 paper which try to understand or answer this concept like mathematically, that why GALU would work for like tasks like language modeling, right? Again, okay, and then once you have done this activation function, so this is the only non-linear transformation which is happening in a transformation in the transformer block. Apart from this operation, every other operation is basically a linear operation. This is the only non-linearity which you add in the transformer block at this point. Because the attention operation, you calculate QKV by doing a linear transformation, then you multiply that, and then you again multiply WO. So basically, you get the output vector by also like then performing a linear transformation on the calculated matrix. Here, the activation function would add a nonlinearity over it, so it would be a nonlinear operation here. Now, in newer models, there are some also the layer norm is nonlinear operation. It's not a linear operation, to be honest. Also, a newer model, like in mixture of experts and other models, they can have like caching and everything, and there can be some different like non-linear operations. But like in this architecture, I think this is the only one. I might be wrong, but like I will check and let you guys
Uh,
know later.
Mehar, can you quickly show the previous slide?
Yep.
Yeah, here we are doing another softmax here, right? That's again a nonlinear.
Yeah, so yeah, again, so this is another nonlinear. So apart from
Yeah.
softmax, like I'm talking about like computation of layer, like what
Hmm.
parameters we are computing and multiplying. So these all are like linear transformations which we are doing in
Yeah.
the
So I
self-attention
don't
layer.
think you would consider softmax as a non-linearity at this point.
Yeah, I mean, it's just a
Um,
probability conversion, like you are converting raw output into a certain range. So it's not a non-linearity because it won't affect the training.
yeah, because it will the softmax will just give you attention scores, right? And which
Yeah,
will be multiplied with the
but
V
again
vector.
with the V vector here,
It would be
which
multiplied
we
on
get
that.
with,
So.
And it also, we will multiply it, the softmax, so the attention probability which we get, we multiply it with W and BO. So again, do a linear transformation over that first.
Yeah. So maybe we will not consider softmax as
Yeah, but again, it's like a squeezing
non-linearity.
function, right? Where you just try to like squeeze the value in certain range. So you convert raw logits to a probability.
Hmm.
So again, but like that's not an operation which we are explicitly doing by learning the parameters, right? Most of that, so the most of non-linearity, or no, most of the non-linear information which you will introduce will come from this, not from the softmax. So that's what I
Yeah,
just
but
wanted to say.
without that softmax, then in the
Yeah,
previous,
so
can you go back
without
to
the
the
softmax, the model won't
max?
work. So softmax is
Like
important.
you can just instead of learning QKV, you can just learn one matrix and then connect the input and the output with one matrix, and that would be equivalent without the softmax, right? So,
No, that won't be equivalent without the softness, because if you have a one vector for QKV, how would you compute the attention score?
can you go back, please? Here, see, so K and Q are two matrices, okay?
Yeah.
Then Q times K transpose is another matrix, right?
Yep.
Then if you okay, then this causal masking is also a nonlinear operation, and softmax is also a nonlinear operation. If you remove these two, then
Yeah.
like W naught is
Then it would be
Q
equal.
K transform, that is just one matrix
Yeah.
that you are learning from K and Q. Then if you multiply W, O, and V, then that's another matrix.
So it is
Then
it is
without this,
equivalent to having an
yeah,
a big
yeah,
matrix
without
without
causal
this
masking
computation.
and
Yeah.
without causal masking and softmax, it will be linear operation. Just
Yeah. Yeah. So I
one
mean,
matrix
these
But
dependent on
are
it.
the
you
non-linear
know, Q
operations.
if you do QK transpose divided by D head and you are just processing one input, then it won't be a matrix, right? That would be just one number. That would be just one number of,
Yeah, but again, the softmax would give the probability over that.
yeah. So the attention
So I
scores
mean,
over sequence.
yeah. So in that case, causal masking would just be the last like layer thing, like a row thing, right? If I just give a one token to it, but again, that would just, so in that sense, it would become a direct path. So you don't
Hmm.
have to do attention, because you always will be doing attention equals to one.
Hmm.
It is as good as shutting down that entire loop in residual stream. And that is what people try to do in logit attribution kind of methods, where you try to trace the path, and there in some cases you get a direct path. So it would be, so if you are giving one token to the model, it is as good as giving it and just doing t projected over WU, because you will get a very similar thing, right?
Hmm.
So yeah, by non-linearity, what I mean is the learned operation here. So these are the operation which are already defined. You're not learning anything in these
Hmm.
operations.
Hmm.
Whereas here you will basically have the parameters, and it will apply a activation function over it. And that's why they say that like the general understanding of the transformer block is that the self-attention layer or multi-head attention basically tries to figure out, or basically have this across connections across different position, and try to figure out like what the information is in the prompt itself. And for example, if I give a text, what is the capital of France, so it will basically, so the output matrix which you will get basically represent the information that I am asking about, the capital city, and that too of a country which is named as France. And the response that it is Paris would basically be triggered by the information stored in these neurons in the multi-layer perceptron layer. So it's like a high level just saying which goes around. The MLP normally introduces like the information is stored in the MLP itself.
Yeah, because the mixing is actually happening in the MLP
Yeah, so
itself.
mixing happens in the MLP. The attention layer is to basically understand the entire prompt and give the entire context and the required task in hand and all those information to the MLP layer. And then what the answer is, MLP will basically try to to calculate that. So in tandem, they work together to try and increase the probability of the final token or the required token. Okay, so moving on, because like I think I have taken around 1.5 hours over the transformers only. So just quickly, this is how it looks connected. So for each position, you have this, you have all the calculations and everything. So I mean, because this was a very complex model, I just tried to decompose it into different blocks. I hope you guys have understood that. So any question in this particular phase? All right, should we move forward? Are we tired? Not.
No,
I'm not sure
no.
what this is. I'm not sure what this is. Is it?
Oh, this is just like for T1 position, you are computing everything. So, for example, for each sequence position, as I said, that the end logit would be T cross D vocabulary. So even
Yeah.
if even if I want the answer on this position, I would be doing the computation on all tokens. So this is like attention. The FNN basically means MLP. So you're doing attention, FNN,
Mm.
attention, FNN for the first token, second token, third token. Then they have projected the attention. So they are L cross H attention to layer and head. You have QK, which is like your attention score calculation. So that is called QK circuit. Then once you have the attention of the probabilities after softmax, the last operation, the Z,
Uh,
that is known as OV circuit. So you have a key query circuit and you have an output value circuit. So those are used to denote the terms, and why they are using is because when you do circuit tracing, which I'm not covering in this presentation, so that's the last so Anthropic is working on that. When you calculate the circuit, you usually try and get those things. So that's the idea, right? All right. Okay, mechanistic interpretability, general introduction. Also, guys, whenever you are tired, just let me know. I know it's a long presentation. Are we good for now?
Yeah, go ahead, please.
Okay. So the general concept of term mechanistic interpretability is to open up the black box of neural networks in general. So mechanistic interpretability is not a new concept which was introduced specifically for large language models. It was there when we had simple artificial neural networks like ANNs. It was there for CNNs. It is there for language models. Excuse me, sorry. Okay. Uh, and the basic idea is to understand the specific mechanism and underlying circuits of the model, which model deploys to compute a response or to come up with an answer. And the assumption is that we can treat all these model as the network which learns some algorithm and reverse engineer that network to see what algorithm it has learned. And the key aspects of this thing is to basically identify the features which are important to the calculation or to the generation process in case of large language model. Map out the internal circuit, for example, which head is active, or the most active 5 top heads, right? Which are active for a particular computation. Because as I say, there are number of neurons, like lot many neurons in large language models. There are also various number of heads. Like for example, GPT 2 architecture uses 8 heads in a layer. So you have 12 multiplied by 8 head, or like H1 has 8 heads, so 1, 1, 1, 2, 1, 3, 1, 4. H2 has all these heads, so you have multiple heads, you have multiple neurons. It's not necessary that they all will learn same thing. So their transformation, the way they will generate the attention scores would be very, very different for each of these heads and neurons. Like how, and that is basically based on what functionality that neuron is learning. For example, or the head is learning. For example, in GPT type models, there are certain heads in the earlier layer which just learn to pay attention to the just previous token or token at just previous position. And the reason for that is that if something is not in the training data, and if few early heads are doing this, from the context, if there is a repetitive task, for example, if I'm saying my name is Mehar Kalra, my name is Mehar Kalra, if that's like 4 or 5 times in the text, or in the context or the prompt which I have given to the model, next time it sees Meher, it tries to predict Kalra next to it. Though it was not in the train data, because of these special heads which pay attention to the just previous token, the Kalra would have been paid attention to the Meher, and the model has learned that correlation in the inference time as well. So while it is calculating the score, it will pay attention to the last token, and that would help model to generate Kalra for the token Meher next time it sees it. So that is a very specific head. So there are 2 or 3 heads in earlier layer in GPT model which tries to do this for induction reasoning, and that is case for all the other models. So all models can do induction reasoning, like they can just learn from the context only and try to predict that, and that's how they come up with. So there are these specific heads which are like a specific head variation or orientation will exist. So we have to map out the circuit that which head is paying attention or which head is basically being active right now, which neuron, which cluster of neuron is basically have encoded this particular information. For example, there are paper where people have tested that there are certain dimensions in the neural circuit or the MLP layers where the information like facts like capitals, a specific fact like country capitals. So when you're trying to ask about country capital to GPT-2, those certain neurons are always active. So they have somehow learned the information about capitals of various countries. So something like that. And this has already been done on the neural networks like CNNs as well. There was the so before we have started on the language model, there was the paper. So there is very good circuit if you want to follow. It's known as anthropic circuit tracing a thread or Anthropic circuit thread, and it has paper since 2023 because Anthropic is like a leading research group in mechanistic interpretability area. Neil Nanda, who is like a pioneer in this area, used to work there. So so the first paper in their thread, I would try to get the link and post it on the packed group, is basically on the neurons or on the information coded in the CNN's layers. So how early layer pay attention to textures and everything, and how later layers pay attention to different shapes and everything. So those layers also learn some algorithm and try to come up with a process or a strategy to predict the answer. So it's not like a miracle or a black box that okay, we give some inputs and we get an output. There, the model actually tries to learn some useful strategies there as well. And then in the end, understanding the algorithm or the transformation and calculation which model is doing in this mapped circuit. So based on that, this is the general methods which are used for mechanistic interpretability of large language model or interpretation of large language models. So we have 2 categories: behavior localization and information decoding. Now, behavior localization is for the feature identification and component identification. So, for example, what tokens in the input have most influence over the output. Like if I change this token, the output is certain output will certainly change, right? Or if I alter this token, the output will go bad, right? Something like that. And then the component of models, like which head is contributing in generation of this particular answer, or in generation of particular task, right? And which MLP is doing that, which layers are active during the generation process. Is the processing done in early layers of the model, or is it done in the later layer of the model, or later layer are only there to just write the result to the next layer, right? So that can also happen. If a task is very simple, it can basically, you can just get to the answer in early layers only, and later MLPs will basically just write down this to the next layer and next layer and next layer. So it would become a direct path after that. So in behavior localization, we have input attribution to basically check which input token or which input position is influencing the generation of the output. Then you have model component attribution. So you have logit attribution, you have causal intervention, and circuit analysis. So I'm not covering circuit analysis today. I would cover logit intervention, logit attribution, and activation patching. So these are two methods to basically localize the components which are responsible in generation of a particular output. Then information decoding is to basically check what the algorithm the model has learned. Like what are the concepts that the model is basically learning, or what the strategies, what the information, what information model has encoded in these heads and neurons, which is helping the model to come up with the right answer. So we have probing, we have dictionary learning and decoding in vocabulary space. I don't think I would be going over this because I think like by the time I would get over with the behavior localization, there won't be much time left to do anything at all. But anyway, so for example, if you're interested, you can look for sparse autoencoders. So sparse autoencoder are basically what they do is they will try, because MLP layer, though it has a size of 4 multiplied by D embedding, still it's a limited number of neurons. So all the neurons are polysemantic. They will encode multiple concepts, right? Or for example, they will get fired for unrelated different tasks. What sparse autoencoder do is to project this information in a very large human understandable space. So they might project this, like say 768 cross 4 would be something around how much? It's 800 cross 4, 16, right?
3072.
Yeah, so it's 3000, around 4000, right? They will try to project this in like a 30,000 dimensional space. So each token will basically, or each value in that space basically correspond to a monosemantic human understandable concept. And then you can see how the neurons are working there. So that's a whole paper on itself. It's a whole area, sparse autoencoder. In this presentation, I'm not touching it. If I get time, I'll just try to schedule another presentation over it later. Anyway, so any question till this point in the concept of mechanistic interpretability and the methods like which I have introduced? Okay. So let's talk about the behavior localization. First is the input attribution. And as you can see, oh, sorry, yeah. As you can see here, this was your input prompt. The movie was absolutely terrible. The acting was wooden and the plot made no sense. I walked after 20 minutes. Now your downstream task is sentiment classification. So you would want to classify this as a negative task, right? So what input tokens are helping you to basically come up with this answer? And like, so for example, terrible has the highest attribution because that's the most negative word here, right? No has a slightly less, but like a very high attribution because it's also a negative word, right? Sorry. So you will try to basically see how these tokens or how the input affects the output, or map the influence of input with the output itself. For example, 20 minutes is not significant for any sentiment classification. It could be 30 minutes, it could be 10 minutes, it could be 2 minutes, right? It can be anything. So, and there are like two ways of doing it. It's first is gradient based attribution, input attribution. The second is perturbation based input attribution. The difference is like very slight. So in gradient based, it's like it uses gradient as the attribution matrix, and what you want. So it's just based on the Taylor expansion of your input, right? So at each point, the gradient, when you do gradient, you will get a direction and you will change your output slightly in that direction and see how the model's output change or how the probability of the logit changes. And then you correlate that and see how sensitive each token is or each element is with the token W, right? Now, this will be done for all the layers. So for each point in the model, you will calculate this gradient. So you will just use an LP norm to basically aggregate this gradient in the end. And then the dot product between this gradient and the input embeddings, if you do, will basically, so input embedding basically tells you the token itself, because when you're processing, your token is a float value or a vector, right? So you will convert this and then you can see which token was having higher or most important influence over your output generation. Again, I would say this is a very vague, or like this was the most layman explanation I have came up with. I wanted to make a demo to show you how this gradient is basically calculated with the model, because there is no other way of explaining it. But as of now, I would just like you can have analogy with like FGSM kind of adversarial attack methods.
So, Meher, what you can do is let's have one another session on this. You just give the overview of whatever you have right now, so you can go deep into that in your next session.
Yeah, I mean,
Because
I
I
was
would really like to know
thinking
about
that,
these.
yeah, I was thinking that would be good, because then next time I won't be explaining the entire transformer architecture, so we can just directly go to the attributions and everything. Yeah, so let me just give you. So this is basically a method. It's very similar to like what you do in FGSM. So you get a direction and you want to just add a perturbation small. So it's similar. It's again, we are adding perturbation, or we're trying to change the input to see how it affects the output. But the change is not like a manual change or a heuristic algorithm based change. It is a change where you have like you just push your value of your input in slide. So you just add a gradient to it. So it would be a mathematical operation. So it would be done in the model. Now, the difference with the perturbation based input attribution is that here you will manually remove or ablate some tokens at different position. So I can basically mask tokens, or I can ablate those tokens. I can set the value of that token to some padding token or like some special token, right? So I will manually do that, or I will have a heuristic which will, or a for loop that runs over the entire prompt and do it for each position, ablate that position, and then see the change in the probability for the uh, output or for the result. And more the change in the probability, the more it decreases. I can say the token causes a big um, uh, in influence. Token has a like a higher influence on the model's output. So this is like a manual way or an easy way of doing it, that you just ablate the token. The problem with this is that you have to come up with the proper ablation then. We have to design the ablation strategy, because if you just replace the token with some random token, that random token also will have its own effect on the model's calculation. So that is one limitation when you try to do this. There are some other methods which if what Arath is saying is correct, I should do another session. I can cover. So they use a contrastive perturbation method. So that's a strategy of like ablating the input tokens. Whereas in the gradient base, it is something like you have an input and just you just push it in that direction. So you are not doing this on the raw tokens or on the input token manually or by using a heuristic or a for loop. It will be done as a gradient addition in while you are calculating the response. So you just push it or just add a gradient to modify the token slightly. The problem with this is that sometimes it just the modification is so slight that it does not even affect the probability. So you might have to do it multiple times to even reach a conclusion. The good part with this is that you straight away will see what the probability change is, because that would be a large probability shift. The problem is you have to come up with a actually good grounded removal or ablation strategy there. And also, a big limitation for the whole input attribution method is that though it will let you know which tokens were which were contributing for the output generation, it does not tell you how model used those token, why the model in the first place basically learned to use those token. What algorithm is there to associate negative with terrible and no? Intuitively we know that it's like a sentiment classification, and if you train a simple NLP based model for sentiment classification, those are the word that those model will learn to pay attention to as well. But why the model has done that, and then what computational steps model is taking to perform this calculation, what components are involved in this. So still we are looking from the outside, we are not in the model. So it's a behavior localization but not model component localization. So the next would be your model component analysis. First here, I would just quickly go over it because I guess it's like 11, 12, 20, 12, 30 right now. So it is nothing but a like logit attribution is a technique for understanding which component of transformer model contribute to a specific prediction by tracing direct effect on the final output logic. So basically, as I stated earlier, residual stream can be can be decomposed into linear addition, right? So you have xi, you have xi plus 1, xi plus 2. And in the end, when I'm multiplying hn or when I'm projecting hn with wu, I can basically say that uh, I will project the embed on WU, I will project the attention output of the first layer. So for if this is for like a 2-layer attention model, right? So you can project that on WU. You can project the output of attention at the first layer at WU. And what I mean by projecting WU is when you project it on WU, you will get a logits, right? And then you can basically generate the probability distribution and see which of these component had the higher probability, like higher association with the output token or with the output predicted. And then we can trace the path using that. So like something like this. So if there is, so there always exists a direct path. As I stated earlier, if there is like no component or no attention head contributing to this, you can have a direct path, or if the attention head is contributing to this, you will have a high association with the probability of a token or like the WU with the attention out, say zero, attention out one, whatever components are basically performing there, right? So it can be a direct path, which is just, so the direct path is nothing but embed projected over the WU. So if you are embedding the raw input or just the H0 residual pre, like you can choose any name, uh, when you project that over WU or you are able to recover the output token, that means the model was actually not doing any major transformation or calculation in the process. If not, then we know that model is using some of these layers as well, or some of these components as well. Big problem with this is that to trace out the circuit or to trace out the component, you have to do it for all the component in the model, which is a very long process. Also, it traces the path, but not tell you what the component's actual contribution was to the output. So I'll quickly go over the causal patching here. So causal patching is another like a upgraded version of trying to localize the model component. And what we do is we swap the activation of a particular component in a single run with another activation and see if swapping of those activation affected the model's output. Because if those swapping, if we change the activations of that particular block or that particular component and it does not affect the model's output, that means whatever calculations were being done by that component or that block is not at all relevant for the output generation. So it has a very basic method. You run the clean, you run a clean run. So you take a prompt, you run a clean run. You take another prompt and you run. So you take another prompt and you run. So we call it corrupted prompt, and you run it. So first of all, when we're running the clean prompt, we will cache the activation for each component. So you will get this cache out from the first run. You run a corrupted run, and while you are running the corrupted run, for each component, you will replace, so you will just apply a for loop, and for each component at once, you will replace its activation with the activation in the clean run and see how the behavior change. Now, there are different ways of measuring the behavior change. So here I will just give you a small, oh, sorry. I would give you very small example. So for example, I was doing this for a mathematical prompt, right? So for example, I had say something like n1 plus n2 equals to r1. That was my clean prompt. Now to see which components were having, so like operand 1 plus operand 2, operand 1, operator operand 2 equals to result. That was the structure of the prompt. Now, if I want to see which of these were basically, which of the attention heads were basically applied to the which kind of position there or which component is basically responsible for result, what I can do is I can have n1 plus n2 equals to some r1, and then I can have n1 dash plus n2 dash equals to r2 dash. And that can be my two clean and corrupted run. I run the clean run. I have the result. So I know what the logit of the result was. I cached all the activation. I run the corrupted run and I switched the activation for each component with the activation from the clean run. Now, what effect that could have on the model? A, because it is coming from the clean run, it can increase the probability of clean result R. At the same time, it will decrease the probability of the corrupted result R dash, right? And third case is it won't have any influence on either of R or R dash. In that case, we know that that component is not paying any attention. So we have an indirect effect where we are saying that is basically the patched probability. So patched probability of R minus the actual probability by PR. So you have that, or so basically either this probability increase or this probability decrease, right? In either way, my component is having an effect over the result. In other words, my component was actively participating in the calculation. And as you can see here, not like, so first one is basically the version where we can't see much because the values were too high. So all the other values were basically somehow uh, like they were not visible at all. But if you see here, you can see that in attention layer was not at all worried about the operands or the operator at all. It was worried about the results, and the results in the medium layer, the component of attention layer. So attention layer, say for attention layer 11 was very active in computation of the result. Similarly, for MLP, we can see the early MLP layer basically tries to encode the value of first operator and first operand, second operand, because that was necessary for the calculation, right? And that is where the information lies. So they tried to basically encode that, and then later on they were also responsible for writing out the result. So this is basically the layer wise localization. So for example, the attention 11 mean the entire attention 11 layer. Not the heads. So all the heads are combined and they're treated like as a single layer here. We can even go more modular and try to do it for each head in attention layer and ML and neurons in MLP. And that's where you can basically see how each component is affecting the output. Now, the way we can measure this behavior change from task to task. For this particular task, because we had two results with us, we can do this kind of IE thing, like indirect effect calculation. In different scenario, you might not have like this kind of formula. You might not use this. You might use some other effect. But the idea is to basically use or basically see what component affects the result and then localize that. Now, this extend on the circuit tracing. So basically, there is something as attribution patching because activation patching also takes a lot of memory. You have to cache the entire activation area and then you have to run it for each component. Attribution patching can be done by using some replacement models. There is very good paper on Anthropic. It's not a paper, it's more like a blog on Anthropic circuit thread. It's known as circuit tracing. So they have traced the entire circuit. Again, so if I will be taking another session on this mechanistic interpretability, because I don't have to go again through the entire transformer understanding, I would try to take that as well. Then, so these, as of now, we have only localized the components, like which components are responsible for the output prediction, what kind of algorithm they implement, what concepts they encode. For that, there are different methods. You can have probing. So probe is nothing but a lightweight classifier which is trained on the model, and it what it will do is take hidden states of each layer and try to classify some tasks. So you have some probe task. For example, if my the downstream task is sentiment classification, I can have a probing task which classify a hidden state as negative or positive, something like that, right? And each hidden layer, at each hidden state, it tries to classify that and understand what information was there. So I can do that. So probing, you can train like very lightweight probes and then integrate them with the model. And while it is running, you can just probe the model at different points and just see what the information was by using a probe task. So you have to design a probe task. That probe task should make sense. And you can train a very lightweight classifier or any kind of very small neural network model to basically see the effect. The second is that the decoding and dictionary space or the vocabulary space is basically something sort of your sparse out encoders. So you will project this on a very so for each hidden states, you will project them on a very large dimensional latent space, which specifically is designed to basically then encode each. The each dimension in hidden state, oh sorry, the large latent space would basically correspond to a monosemantic human understandable concept. And then you can see what concept that neuron was basically trying to embed. But again, you have to train the entire sparse autoencoder, and that's a whole process in itself and a whole idea. That's a whole the sparse autoencoder have their own architecture. So if I have to go through it, that would be another meeting session then. So for this presentation, I would be stopping here. If you have any questions, we can have a discussion. I'm sorry, I have taken a lot of time.
Thank you, Mayor, for such a great presentation.
I hope you guys liked it. Sorry, I was not able to get the demo up and running. So I know because these are just methods, so you can't understand much into them without like seeing how they work or like what they basically bring to the table in the end. But yeah, I can take another session on this later on sometime in like early March, and we can try to just go over this again.
Exactly. I would like to see the different approaches that are out there
Yeah,
of
sure. For
mechanistic
sure.
interpretability, like go deep into them and see like how exactly they are working and what
Yeah.
are the outputs you're getting.
I'll try to get some demo running so we can see like how input attribution is calculated and how it's like correlated with the output.
Yeah, thank you so much. It was so insightful and like we learned a lot, I guess, like in depth, like how is it working out. So thank you
Yeah,
for
Yeah,
that.
yeah, very
And
nice
yeah, I would
presentation, Meher.
also be really
Thank you.
interested to know
thank you so
like
much.
yeah, how perturbation things work out and how can we get the tokens which are actually making sense in the prediction. Like that is the main goal, right, for
Yeah.
interpretability.
That's
So
the
yeah.
input attribution. And
Mm-hmm.
then you have logit attribution,
Mm-hmm.
causal tracing, and then
Mm-hmm.
you have circuit tracing in the end. So
Yeah.
that formulates the behavior localization.
Yeah.
Once you have localized the behavior, you want
Mm-hmm.
to understand the algorithm of the circuit, then you
Mm-hmm.
go to sparse autoencoder or like
Mm-hmm.
probing methods like them. So yeah,
Mm-hmm.
it's like a step-by-step end-to-end package in itself,
Yeah.
the interpretability methods.
Agree.
In order to understand a model, you can't like apply just one or two methods. You have
Mm-hmm.
to do an entire process for it.
Yeah.
So yeah,
Would love to
definitely
learn.
I'll just try
Yeah.
to go over it. And thankfully, like we don't have to go over the architecture again because I think that has taken a lot of time.
No, it was good. Thank you so much. Yeah.
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 Wonderful session.
Okay. Yeah.
Yeah,
Welcome.
Meher.
Welcome.
So
Yeah, hi.
thank you very much for the presentation. So like I tried learning transformers by reading the original paper and watching videos, but like it is today that I got actual understanding about how it works. So thank you. Like after today, I won't be able to tell you that I don't understand this. Please excuse me. So
No problem. And also,
you
like,
explain it to
just
that level. So thank you
you
very
can
much.
cross-check this like with papers because also I am in the learning mode. So please
Yeah,
get questions, get as many questions as you guys can, and then we can just
yeah.
collectively try to figure that out.
Yeah, yeah. Thank you very much. And like as others mentioned, like for the mechanistic interpretability, maybe we'll have another session because like when after you started that, like my brain experienced an overflow and like I wasn't like there was
Yeah,
too
I know.
much information in the same
I
session,
know
so
it's like
I
a
didn't
lot
get
of
everything at
information.
the end. So maybe we can have another session and so we can understand them in detail. Thank you very
For
much.
sure,
Thank you.
for sure.
Yeah.
Thank you guys for joining. Thank you so much.
Thank you, Mayor.
Thank you. Welcome.